Okay, so in this question, we're going to look now more specifically at the graphite structure of carbon, whereas in the previous question we looked at diamond. In graphite, each of the carbons is bonded this time to 3 other carbon atoms. Bond angle 120 degrees between each of these carbons, which can then obviously bond to more carbons. Each one, as we just said, bond into 3 other ones, covalently bonded, okay, giving us a planar structure based on a hexagonal motif. Okay, so you get a kind of structure resembling that. So, as we said, each carbon is tetravalent, which means it has 4 outer electrons which are available for bonding. But obviously, in graphite situation, it's only actually bonding to 3 other carbons, each of these being a pair of electrons, which means that each carbon has actually got a spare one. There's 1 electron on each of these carbons, which is free. And as we've seen with metals, in a similar fashion, this electron is delocalized. Obviously, this is not metallic bonding because carbon's not a metal, but the electron is delocalized, and in a similar fashion to metallic bonding, that delocalized electron allows carbon graphite to conduct electricity, which interestingly allows us to answer the second question probably easier than, or more quickly than the first one, is because the graphite, or the presence of the delocalized electron, is the key thing here. The delocalized electron, obviously, it gives it its ability to conduct electricity and gets you the first of the 2 marks for this question. But the delocalized electron can move through the structure, and it's this kind of supplementary part of the sentence which a lot of people miss off and subsequently miss the second mark. So the delocalized electron can move through the structure, and that's what allows it to conduct electricity. So it's this, as we say, this second part of the question here, of the answer here, that can move through the structure, which you need to just get used to adding on to the end of that question just to pick up the second mark, even though you knew it was about delocalized electrons. So going back to the first part of it, though, we've got, obviously just get the marking points for this one now, we've got 3 covalent bonds. Okay, we've got the 3 covalent bonds giving us a hexagonal structure, giving us a 2-dimensional planar structure. And it's these planar structures which then gets us into the last part of what graphite does, is if we imagine each of these carbon layers that we have here, which I'll just take away, is if we then rotate this molecule and rotate it through 90 degrees. So instead of looking on from the top of each of these sheets, what we now do is we're going to look along the side of one of these. So we see each carbon now looking along the side of it. We're going to see the planar structure. But what we don't see now is any covalent bonds in the upward direction or the downward direction. There's nothing appearing here. There's nothing appearing here in terms of covalent bonds. What we see is just another layer of carbon graphite. We see a second layer underneath. We see a third layer underneath, etc., etc. But there's no actual covalent bond existing between these layers. What we have here is a very weak intermolecular force of attraction. Okay, this force here exists, but it's very weak. Okay, it's a very weak force. It allows graphite to have some interesting properties. It's quite strong in the 2-dimensional direction of the layer, but then between the layers, it's actually quite weak. Okay, it's got a weak force of attraction. Okay, it's an intermolecular force of attraction between those layers. Okay,